Miss the pigeons. I wonder how they're doing. Let's do a problem. So, moving on to relative motion analysis, we have a series of rods that are connected at these various points, and then we have this slider moving at C that is moving purely vertically. So, as we had noted before, the basis for all relative motion problems is a relative position equation. So, we have these 3 points A, B, and C. Point A is going to be our fixed point. That means rod AB is having a pure rotation about point A. And then we have this rod BC, which is undergoing both a rotation and a translation. And then we have this slider C that is moving purely vertically downward. So if we were to write down a position expression for it, we would have that the position of C relative to A would be equal to the position of C relative to B plus the position of B relative to A. So again, thinking about these vectors here, we're saying there is our B slash A, here is our B slash C, sorry, C slash B. Then the position vector of C relative to A would be a vector that stretches there, and then this velocity vector that we're trying to find, VC slash A, is just the derivative of that vector. So starting from this relative position equation, we have a relative velocity equation just by replacing all of our R's with V's, and this gives us V, B slash A. So, looking at each of these motions then, we have the motion of B relative to A. This is going to be a pure rotation. We have the motion of C relative to A. This is going to be a pure translation. And then we have BC, which is undergoing a rotation and a translation. However, we're only looking at the motion of C relative to B. So if we were riding along on point B, then we would just see point C undergoing a rotation because it's got some fixed length away. So, in fact, both of these terms are going to represent rotations about some point. So, if we were to look at these in pieces, we would, for example, have our velocity of B relative to A to be equal to some angular velocity vector omega AB crossed with our B slash A. So that was the expression we had in the book for something undergoing a pure rotation. We're going to have a similar expression for our C slash B. That's going to be some omega BC crossed with our C slash B. Now, that new angular velocity, omega BC, is going to be an unknown. We're given what omega AB is, and we're trying to solve for VC, but omega BC will come along for the ride as another unknown, and then these two position vectors we can write out using these lengths and using these angles. And then later we will plug in the given values that theta is equal to 60, phi is equal to 45 degrees. So for the moment, we just have some grunt work writing down what all of these vectors are. Notice our angular velocity vectors, since everything here is in a plane, we're going to have that omega AB is just equal to the magnitude of omega AB, which is 60 radians per second, multiplied by k hat. Our vector RAB is the one that stretches from A to B, so it's going to have a negative x, positive y coordinate. So our B slash A is going to be equal to negative 300 millimeters times the sine of theta times I hat. That's the negative x component, plus 300 millimeters times cosine theta, let me make sure I'm not writing off the edge here, times j hat. So we take the cross product of those two vectors, noting we have k cross I, which is going to give us j, and then k cross j, which gives us a negative I. So putting those together, we have v b slash a, which is omega ab crossed with r b slash a, and that's going to give us First off, 18,000 millimeters per second, and then in terms of the components, we have negative I hat cosine theta minus j hat times the sine of theta. Again, that omega v slash b, since this is a pure rotation, would just represent a velocity going purely in that direction. We do something similar for the next rotation. We have omega bc is equal to, again, some unknown magnitude, omega bc times k hat. We have our c slash b, which again we can figure out using those components. That will be equal to negative 600 millimeters sine phi times I hat plus a negative 600 millimeters times cosine phi j hat. Then form the same cross product. We have v c slash b is equal to omega b c crossed with r c slash b. Again, we have the k cross I term, the k cross j term, and that is going to end up giving us 600 radians per second omega bc cosine phi I hat plus a negative 600 omega bc sine phi j hat. Okay, so we've got those there. Now, we can then take those two expressions and add them together to get our vc slash a. Now, it looks like, well, it's actually true, we have this one equation. However, we have two unknowns that have now cropped up in this problem. We have this omega bc, this new quantity that we've introduced, as well as this vc. However, this one single vector equation means that we have a component in the x and a component in the y, which means that we really do have two equations. We have an x component equation and a y component equation. And notice that our vc slash a is only moving in the y direction, so we can write that as negative vc times j hat. So then putting together our equations in both the I hat and j hat directions, in I hat, our vc slash a has 0 component, so that's 0. For the other side, we take our I components of each of these terms. So this I component gives me negative 18,000 cosine of theta, and I'm going to go ahead and plug in 60 degrees, and then take the I component here, plus 600 omega bc times cosine of 45, plug in that angle. Notice immediately that's going to give us enough information to solve for omega bc. We'll come to that later. Let's write down our second one. This gives us negative vc, because I've already said this is negative, because I'm looking at just the speed with which it's going down. This is equal to negative 18,000 times the sine of 60 degrees minus 600 omega bc times the sine of 45 degrees. So once we find omega bc from this top equation, we then plug it into the bottom equation. So doing that, we get omega bc is equal to positive 21.2 radians per second. So that's giving us a counterclockwise rotation in the same sense as the rotation about A. Then plugging that into the second expression here, we get that v sub c is equal to 24,588 millimeters per second, and we'll move that up to a more sensible 24.8 meters per second pointing downward. And I really think the pigeons would have liked that problem. See you next time.